Just when you thought there couldn't be any more parts to this lecture, part 5 of our introductory session on base R programming, matrices and arrays. Attributes are extra information that can be attached to an R object. To view the attributes of some object X, we can use the command attributes of X, and we will get a null if X has no attributes. Names are an example of an attribute. So if I take the vector 1 to 5 and I check its attributes, I'm going to get null. But if we return to the example from an earlier segment of this lecture, with my birth year, my slightly inaccurate age, and number of siblings, we'll see that this particular vector has attributes, namely it has names. So here they are, birth year, age, and siblings. The reason I have introduced attributes is because a matrix is simply a vector with extra attributes, namely dimensions. So dimension is an attribute. You can view the dimensions of something by using the command dim. Atomic vectors have no dimensions. If I return to my x is 1 to 6 example and take dim x, I'm going to get null. But if I give a vector dimensions, then suddenly it becomes a matrix. So here I'm going to take x and I'm going to assign it dimensions. Namely, I'm going to assign dim of x gets 3, 2. The first of these is the number of rows, so there's 3 rows, and the second is the number of columns, so there's 2 columns. And now we see that my vector 1 to 6 has been turned into a matrix. And notice that the way that R is filling in this matrix is column by column. So going down the first column, we have 1, 2, 3, and going down the second, we have 4, 5, 6. I can't possibly repeat this enough. A matrix is just an atomic vector with dimensions. What that means is that matrices actually inherit some of the key properties of atomic vectors. First, they only store elements of a single type. Second, they operate, or rather the standard mathematical operations work on them element by element. Third, vectorized functions are also very often going to work on matrices. And fourth, matrices are also subject to the recycling rules that we've already spoken about. An array is a higher dimensional generalization of a matrix. And if you're familiar with Python, in Python, there's a machine learning package called TensorFlow. Sometimes higher dimensional generalizations of matrices are called tensors. In R, they're just called arrays. Okay, so matrix and array operations are in general very, very, very fast. And that's why we like them. Okay, so adding or changing dimensions doesn't change the type of an object. If I start off here with x gets 1 to 6, which is just the vector 1, 2, 3, 4, 5, 6, and I ask what is the type of x, I'm going to get integer. Now you may be wondering, I said in an earlier segment of this lecture, hey, the default numeric type in R is actually not integer. Well, the reason why this is actually producing integer is because that shorthand with the colon, 1 to 6, you see I have 1 colon 6, that actually defaults to producing an integer. But that's more trivia than anything else. It's not very important. Let's take a look at dimension once again. So the dimension of x, dim x gets 3, 2. That's going to change x from being an atomic vector to being a matrix because we're setting the dimensions. So what happens if I check the type of x? Well, it says integer. So it seems like nothing has changed. The type of x is unchanged. But that's not the case. The type may not have changed, but the class has changed. So if we calculate, or rather, if we evaluate the class of 1 to 6, we're going to get back integer. Whereas if we evaluate the class of x, we're going to get back matrix array. So there is something that changes when we assign dimensions. It's not merely that we've created attributes. It's also that R recognizes that because there are now these new attributes, because there are now dimensions, it's able to operate on this object X in a different way than it could before. So in particular, matrix operations are now going to make sense for this object X. Which brings us to an important caveat. A vector is not a 1 by n matrix, at least not in R. This is a very, very, very important distinction. We'll return to our favorite example again. X is 1 to 6. We can check the class of X. We can see that it starts off just as integer because initially it's not a matrix, it's just an atomic vector. Now we're going to set dimensions 1 and 6. So the number of rows will be 1 and the number of columns will be 6. Here's X again. If we check its class, it is now a matrix. A matrix is a form of an array, because remember, an array is a higher dimensional generalization of a matrix. So that's why it says matrix array. And the way that R prints out X has changed. Notice that towards the bottom of the slide, we have these more complicated bits of bracketing, 1, 2, 3, 4, 5, 6, above the elements of the matrix. Whereas at the very top of the slide, we did not have this. So a vector is not a matrix, and this is important because some R functions and operations are only going to work with matrices. So again, remember, attributes and class matter. When I say that a vector is, rather a matrix is merely a vector with attributes, that's true, but those attributes change the kinds of things that you can do with it. And as I mentioned before, R fills matrices by column. So what does this mean? We saw that one way to create a matrix is by setting dimensions. So now if we take X is 1 to 9, and we set the dimensions to be 3 by 3, 3 rows and 3 columns, R will fill out a matrix column by column as 1, 2, 3, 4, 5, 6, 7, 8, 9. Another way to create a matrix is by using the matrix command. So the matrix command requires 3 arguments, the data, n row, and n col to specify the number of rows and the number of columns. Here, data is an atomic vector. And we see that we're getting exactly the same result as above, but by a slightly different means. Now, again, by default, R fills matrices by column. If we want to override this behavior so that it fills them by row, we can do that. We just need to set the option by row equals true, as I do in the example below. And here we see that R is filling the matrix up not top to bottom, but left to right. 1, 2, 3, 4, 5, 6, 7, 8, 9. If we want to check the number of rows or columns in a matrix, we can use the commands n col and n row. Here's a little example with the chess pieces from earlier. I can check how many rows are in this matrix of character data. The answer is 2. I can check how many columns there are. The answer is 3. And notice that this is exactly the same information as I get from dim. It's just a bit more convenient, perhaps, if all I really want is the number of rows, to extract that directly and not have to get both the number of rows and columns at the same time. There are lots of times in econometrics when we want to work with a diagonal matrix, and R has a command for this. The command is diag. For some vector x, diag x constructs a diagonal matrix out of x. The way it does this is by taking a square matrix of zeros and putting the elements of x down the diagonal from top to bottom. So here we have a diagonal matrix with elements 1, 2, 3, 4 on the diagonal. But diag can also be used to do the opposite. So if you have a matrix, diag extracts the main diagonal. Now that I've created this matrix M using my first use of the diag command, I can apply diag again, and now I'm going to pull out the diagonal elements of the matrix, basically bringing me right back to where I started. If you just want the identity matrix, you can also use diag to get it all you have to do is specify diag and then the number of rows that you want. If you don't specify the elements, R will actually default to giving you a diagonal matrix. Or rather, I should say, if you don't specify the elements of your diagonal matrix, R will simply default to giving you the identity matrix. So how do we access elements in a matrix? Well, it's the same idea as vectors, but it's in 2 dimensions. So we still use brackets, but now we've got to refer to both the row and the column positions. So here is a matrix M, which I am going to fill up with the numbers 1 to 16. It's a 4 by 4 matrix. To access the 3, 3 element, which is 11, I can use M bracket 3, 3. If I want to pull out rows 1 and 2 and columns 3 and 4, which is a little submatrix of M, I can do it as follows. M bracket 1 colon 2 comma 3 colon 4. And that pulls out the upper right-hand submatrix of M, which contains the values 9, 10, 13, 14. We can also subset matrices using logical vectors. And here, this works very similarly to the way that it did for atomic vectors. So we have to specify a logical vector that is of the same number of rows in the first position before the comma, as R has rows, and the same number of columns in the second position after the column. I should say the second vector has to have as many columns as M has. The first vector has to have as many rows. So again, the syntax for accessing elements of a matrix in R is we specify the row information before the comma and the column information after the comma. Just as we saw with atomic vectors, when you want to use logical values to subset, they need to be of the same length as the whole object. Whereas if you just want to use indices, vectors of indices, they don't have to be. So this kind of naturally generalizes what we saw with atomic vectors to the case of matrices. If you don't specify brackets, that means you're going to get everything from a given dimension. I should say, if you don't specify any brackets, you're going to get the whole matrix. If you specify brackets, but you leave one of the elements empty, as we see here, M of 1 comma nothing, then you're going to get everything from that particular dimension. So here I said M bracket 1 comma, and this returned 1, 5, 9, 13. That's a way of telling R, I would like to have the first row and all of the columns. Alternatively, if I specify M bracket comma 4, that's a way of telling R that I want to have all of the rows, but only the fourth column, which is 13, 14, 15, 16. And notice that when I pull out a row or a column, R is returning an atomic vector. So 1, 5, 9, 13 is an atomic vector. So is 13, 14, 15, 16. I can use a similar idea with logical subsetting. Here I'm going to subset the columns of M using the vector of logicals false, true, which says, hey R, exclude the first column, include the second, exclude the third, and include the fourth. But because there's nothing before the comma, I'm including all the rows. So you see that this is just a way to return columns 2 and 4. The commands rbind and cbind can be used to create or to expand a matrix by binding rows in the case of rbind, or binding columns in the case of cbind. So let's take a look at a little example. I've got a few vectors here, x, y, and z, and I'm going to cbind them. I'm going to column bind them to create a matrix M. You see what happens? The vector 1 to 3 gets put next to the vector 4 to 6, which gets put next to the vector 7 to 9. I could also have R bound, or R binded perhaps, the very same vectors. If I did that, then everything is turned on its side. So rbind takes some vectors and installs them as rows of a matrix, whereas cbind installs them as columns. You can also use cbind and rbind to attach one matrix to another. So in the top right-hand side of this slide, I have cbind of m, comma, diag n row equals 3. Diag of n row equals 3 gives me the 3 by 3 identity matrix. So what this command achieves is to build a matrix by putting a 3 by 3 identity matrix to the right of the matrix M that we already created. We can use a similar idea to stack matrices on top of each other using rbind, as you see in the bottom right of this slide. Now it's time for another example. As usual, take all the time you need, try your hand at these exercises, and check your solutions against those on the course website. Here's some code that doesn't do what was intended. This is a failed attempt to produce the 3 by 3 identity matrix. So in line 1, I'm going to assign the value 3 to the variable n. In line 2, I'm going to create a matrix that I'll call I, EYE, and this is just a matrix of zeros. Just below that, I'm going to attempt to set some values in I to 1. So what have I done here? Well, I've done I of 1 to n, comma 1 to n, and I've set those to 1. So what is that going to do? Well, maybe you'd think that's going to produce an identity matrix, but actually it's not. What it's going to do is it's going to select all the rows from 1 to n of this matrix, all the columns from 1 to n of this matrix, and then it's going to assign 1 to each of those elements. That was not what we wanted to do. So instead, what we could be doing here, if we wanted to construct that identity matrix, is we could subset one matrix using indices from another matrix. This is a little more complicated, but it can be very, very, very helpful in practice for constructing complicated matrices with special sorts of patterns in them. Here's how it works. The first couple of lines are exactly the same as before, but lines 4 through 7 do something a bit different. I'm going to construct a matrix called elements. And this matrix is going to contain row and column indices. So what do I mean? Well, what I mean is, if you look at the way that I construct elements in line 6, and you look at the actual matrix elements that I print out after line 7, take a look at the first row of elements. It's 1, 1. I've set that up because I want that first row to refer to the elements of another matrix. So that first row of elements is going to refer to the row and some row and column position in some other matrix. The second row is going to refer to some row and column position in another matrix. The third row is going to refer to some row and column position in another matrix. So what I'm trying to do here is I'm trying to represent the idea of the main diagonal of a matrix by using this other matrix, elements. If that all seems very confusing, the example may help. If I take I, my wannabe identity matrix that hasn't got the ones on its diagonals yet, and I subset it using this matrix elements, I should say, and I assign to 1, look what happens. I get exactly what I want. So this is actually a very useful way of accessing elements in a matrix. You just first set up one matrix whose first column is the row positions, and second column is the column positions that you want to index, and then you subset another matrix using that. All right. Now we're ready to start doing a little bit of math with matrices. So again, a matrix is just a vector with dimensions. So that means that addition, subtraction, multiplication, and division are all element-wise just as they are for atomic vectors. So if I have a matrix M, which I construct as follows, and I have a matrix R, which I construct as follows, both on the left-hand side of the slide. I can add them together on the top right-hand side of the slide, M plus R. I can subtract them, M minus R. I can multiply them, and I can divide them. Now, M plus R really is matrix addition, just like M minus R really is matrix subtraction. But M times R is not matrix multiplication. Take a look at what's going on here. I am not multiplying these matrices together. I am multiplying their elements together. I'm multiplying to get the product M times R. The 1 element of that matrix is 1 times 0. Similarly for M divided by R. If you're coming from MATLAB, you may find this strange. Some other languages potentially as well. But because a matrix is just a vector with dimensions, the operations multiply, divide, add, subtract behave exactly as they would for vectors. If you do want a matrix product, don't worry. R's got you covered. And I should just clarify that this is not going to be a comprehensive introduction to matrix algebra in R today. It's just going to be some very basics. We can multiply matrices. We just need to use a slightly different operator. So I'm going to set up on the top left of the slide, I'm going to set up a matrix A, and I'm going to set up a matrix B. Now, in the bottom left of the slide, I'm going to compute the element-wise product of A times B, just like on the previous slide. But now I am going to construct a matrix product. So let's take my vector 1 to 2. To take the matrix A and matrix multiply it by V, so A matrix multiply V, I just put my multiplication sign in between two percent signs. We've already seen the percent signs once before. We saw them with the binary operator in, which is used to find the indices of one vector in which the elements of another appear. Here, we wrap the multiplication symbol in the percent signs to turn element-wise multiplication into vector multiplication. And here, while V is an atomic vector, R promotes it to a matrix for the purposes of the multiplication. So you can actually just write A matrix multiply V. Even though V is an atomic vector, R figures out what to do. If you want to get the outer product, so that would be a vector multiplied by its transpose, you can do that as well. R will, again, promote V to a matrix, and it will interpret it as a column matrix. To get the outer product, you take the letter O, and you enclose it in percent signs. Matrices can have names too. Here's a little example in which I construct a matrix of temperatures in different locations in the UK on a series of days. And I give the matrix row names and column names. To do this, I can use the commands row names and the command column names. This can be helpful for making the results of some R function easier to read and understand. And as we saw with atomic vectors, names can also be helpful as a way of selecting things. Just as we can subset atomic vectors by name, we can also subset matrices by name, assuming that the matrix has one. Now, you may want to look closely at the examples on this slide, in particular, the very last one. There's something slightly funny going on there. Have you spotted what it is? Well, let's take a look at our temps matrix. So the columns are days of the week, the rows are locations, and the elements are temperatures. If I run the command temps bracket Aberdeen, comma, I'm going to pull out the row whose name is Aberdeen, which is the first row. So I get 5, 2, 2 with the column names Monday, Tuesday, Wednesday. If I instead run the command temps, comma, weds, I'm going to be pulling out the column Wednesday, which has the values 2 and 8, 2 for Aberdeen and 2 for Plymouth. But you might be surprised that R is actually displaying this not as a column, but as a row. And the reason is that R has actually demoted this column of temps to an atomic vector. And this is because of a strange convention in R called drop. Drop, in effect, deletes extra dimensions. So taking a look at the top left-hand side of this slide, the example from the previous slide, temps, comma, weds. Well, what exactly is this? This is actually the same as specifying the argument drop equals true. That's the default in R. To see what drop equals true does, let's set it to false. So I'm now going to add another comma, and this funny looking command, drop equals false. Now, R is not dropping this extra dimension. R is instead displaying the results as a column. So what's going on here? Well, what R says is if I take a matrix and I only ask for a specific column, then I don't really need to represent that using a matrix. It's only a one-dimensional thing. It's not two-dimensional. So R says, there's no need to treat this as a matrix any longer. I'm going to drop the extra dimension and just display it as an atomic vector. If you don't want that behavior, you have to explicitly ask for R to not do it. The way you do that is by using the command drop equals false. On the top right of the slide, I have another example to make this clearer. I have specified a matrix which is 1 by 4. Again, that is not the same thing as a vector because we can check that it has dimensions, 1 and 4, and its class is matrix array. Now, we can construct V to be drop of M, and if we do that, what's happened? Well, we have exactly the same numeric values, 1, 2, 3, 4, but now the dimension is null. We got rid of the dimensions, and the class is integer, so it's no longer a matrix. And now we have a big, beefy exercise for you to play with. This one may take you 15 minutes. It may take you a bit longer. Please pause the video, work your way through it, and check your answers against the ones on the course website.